Hello and welcome to EP2CM4 topic number 6 on thermal expansion. This topic we're going to explore how things change in size in response to temperature change and how to simultaneously model this size change along with the size change from applying stresses that we were dealing with before in a mechanics course. So first of all, recall that strain is caused by stress through Hooke's law. That is, the strain epsilon is caused by stress sigma through Hooke's law, which is a linear relationship. So if epsilon is a vector of the strain components in the axial and then the shear direction, this is using Voigt notation, that would make it a 6x1. And the stress is also a vector of the of size 6x1 that includes the axial stresses in the first three and then the shear stresses in the other three. Then the relationship between stress and strain is through the stiffness matrix here, if you want to say stress is equal to something times strain, or through the compliance matrix S, if you wanted to find the strain directly from a stress. So stress causes strain through multiplication by the compliance matrix. But that's not the only thing that can lead to strain. If you heat up an object, then you'll find that it also gets a strain developed according to alpha times delta T, where alpha is the linear coefficient of thermal expansion and delta T is the temperature change from whatever we're going to define as the original dimensions of the object. So we could say that the total strain is this first strain, compliance matrix times the stress, plus the new strain, the thermal strain, alpha times delta T, where you might call this first part the mechanical strain, and you might call this second part the thermal strain. So let's think for a moment about where these strains come from. The mechanical strain shows up ultimately because the atoms inside a solid are held together by the Coulomb force. So when you pull on them, then that extra force is going to lead to a little bit more displacement between the atoms on average, and that's how you get to a strain from that. Thermal strain shows up because the atoms are not just holding still in these spots. It's really like a bunch of little masses on springs. So they're oscillating around, they're kind of bumping into each other, really held in position more or less by the Coulomb force. But if they've got more temperature, being more average energy per degree of freedom, degrees of freedom including these vibrational degrees of freedom that show up in a solid, then they're moving a little bit faster on average, they're pushing on each other harder, and they're going to be happier being farther apart even when you're not applying any stress to it. So an object in space, if it's at like a higher temperature, then it's going to be farther, it's going to be larger, right? You increase the temperature, it generally gets a little bit bigger, assuming alpha is positive, as it almost always is. There's some interesting exceptions where alpha is not quite positive, and that's increasing temperature makes the object get smaller. But in general, because of this model of how solid atoms work, when you increase the temperature, it gets larger even if you're not applying any stress. So sometimes it's more convenient, rather than dealing with the strain directly, to rearrange this and find what the stress would be. So we can solve this for stress by first taking the alpha delta T over to the other side, and that'll look like this. And we've got compliance matrix times the stress is equal to strain minus coefficient of thermal expansion times the temperature change. And if we want to get rid of this compliance matrix, we can left multiply this equation by the inverse of the compliance matrix, which is the stiffness matrix. So that'll leave us with sigma is equal to C times epsilon minus alpha delta T. This thing, epsilon minus alpha delta T, is the mechanical strain that we had earlier. So in this situation, it's the regular strain, the total strain, minus the thermal strain. So that's S sigma is also the regular epsilon minus the thermal strain alpha delta T. Or we could just leave it in this form, epsilon minus alpha delta T, and carry this stiffness matrix through to come up with this new term, C times alpha delta T. Normally, we wouldn't define this as its own quantity, but if we were going to be dealing with stress in this form, then this is just another vector, right? So the stiffness matrix times alpha will give you a different set of thermal expansion parameters, where now they don't tell you directly what the strain is after multiplying by temperature change, but they tell you what stress would be created in a situation where you're holding it still per change in temperature. We'll look at an example. Suppose a rectangular prism gold bar has dimension 30 centimeters in X by 10 centimeters in Y and 8 centimeters in Z, and we want to find the axial stress that's required to compress it by 1% in X, assuming it's free in the other directions, the temperature change that's required to extend it by this amount in X, the stress if it's held still in X during this temperature increase instead. So imagine if we hold it still in X, we don't let it increase, then how much? We don't get strain from the temperature increase, we'll just get stress. And then how and why the answer to this part would be different if we held it still in all the dimensions during this temperature increase. And finally, how much the weight and market price is of this bar of gold. Then we're going to repeat this for a similarly sized bar of aluminum 6061 and ice. So the first part, which you can skip if you're not into that sort of thing right now, is looking up material parameters. So here's a table of all of the material parameters. A lot of these are from Wikipedia, except for a few different ones. Ice is a little bit complicated to nail down the parameters of because there's a lot of different kinds of ice and how you'd form the crystal structure. So natural ice isn't quite as perfect as you might be able to make ice in a laboratory, so the Young's modulus exists over a wide range of values. And similarly for the Poisson's ratio, but the thermal expansion coefficient is a little bit more consistent, interestingly. We also have market price looked up at different spots. So this is based on a bag of ice from Walmart. This one for aluminum is based on a one particular value for a block of aluminum 6061 that I found on Alibaba. And this one for gold is at the time of looking it up in February 2020. If you were to look this up today, then you will probably find that the price of gold is likely even higher than this, unless you're watching this in the distant future, perhaps, where there's been a massive change in the value of the dollar, like a massive amount of deflation, coupled with some nuclear process revolution that makes it a lot easier to create gold rather than having to rely on it being created in supernovas. So the first part, axial stress required to compress it by 1% in X. Let's look at the simpler version of how to do this at first. So if it's free in different dimensions, then you can relate a material's stress and strain through the simpler version, that sigma is equal to E times epsilon. This is only true if it's totally free in the other directions. Otherwise, you'd have to use the more complicated expressions from involving the matrices that we were just looking at. So for an isotropic material where we can actually just talk about a Young's modulus rather than having to specify a direction for it, we can say that sigma is equal to E times epsilon if there's no temperature change. If there is a temperature change, we can work with the rearranged version of this. Epsilon is equal to 1 over E times sigma plus alpha delta T. This is like the one-dimensional version of this problem, which is going to be okay for parts A through C, but we'll have to get a little more complicated for part D. Okay, so if we rearrange this, you can see how the temperature change will factor into it. It's going to end up being this minus alpha times delta T. So the first part, if we have no temperature change and we want a 1% compression, then we're going to need sigma to be negative 1% times E. So sigma in part A is going to be negative 1% of the Young's modulus of gold, or negative 790 megapascals. The temperature change that we would need for this strain to happen, we can return to the first equation maybe and set sigma equal to 0 and see that the temperature change would be epsilon, 1%, divided by alpha, 14.2 E minus 6. If you were to divide those two, then you'd find that at 704 degrees Celsius of a temperature increase, or 704 Kelvin. This being an inverse Kelvin. After you divide epsilon, which is unitless, by alpha, then you'll have Kelvin back. Okay, and the next part, suppose that you hold it still, you make the strain equal to 0, then the stress that we calculated in part A, which by itself with no temperature change led to 1% compression, and the temperature change from part B, which led to a 1% expansion, would add together to create 0 on this side. So we'd expect that if we increase it by the same temperature change while holding this to 0, then the stress that shows up should be the exact same stress that we got from part A. Okay, so that's the solution for parts A, B, and C. Let's look at it with a little bit more detail. So reminder for this first instance, when we have no temperature change and we're looking at the strain, this is a typo here. We're looking at the stress that would lead to, that would show up from a 1% compression. Then that stress is E times epsilon. Well, how do we reconcile that with the picture of the full kind of matrix equation in Voigt notation that we had earlier? So when we're saying that the strain is equal to compliance matrix times sigma plus alpha times delta T. Well, for an isotropic material like these metals in non-single crystal form, or this like amorphous solid here, ice, where it's the same in every direction, we don't have anything special going on in X versus Y versus Z material parameter wise. So you expect the matrix to have this kind of a form in symmetry. This is the stiffness matrix that we calculated for this type of material after introducing what Poisson's ratio was and how it couples one axis to another one. So you might remember this from a mechanics course. And for the shear stuff, it's just the shear stress is equal to the shear strain multiplied by the shear modulus, where shear modulus, again, only for an isotropic material, is equal to E over 2 times 1 plus Poisson ratio. If you were to combine this stuff into a full 6x6 form, then we have this kind of symmetry for the isotropic material in the matrix, and substituting in these components directly gives us this full list of parameters here. A lot of this stuff is similar from one component to the next, so it's probably easier to calculate it if you first factor that stuff out and just leave the Poisson's ratio stuff inside. But this might be a little bit, I don't know, it probably is more readable because it shows off what's similar, but any one component you'd have to multiply this constant through before you carry it over. Okay, if instead the material's otherwise free, this is good if it's otherwise fixed, because then you can set all the strains except for the one you're concerned with to 0 and multiply this across and see how the stress in that direction is related to the strain directly. But if it's otherwise free, then we've got all the stresses except for sigma x equal to 0. That's the first case in part A. In part D, we're going to be having all the strains equal to 0, but for part A, B, and C, all the stresses are equal to 0 except for sigma x. So we can see that epsilon x is just 1 over E times sigma x in that situation. Let's actually do that. So all the other stresses are 0. So when we have that the strains are equal to compliance matrix times the stress plus 0, looking at the compliance matrix from above, we'll have that it's the 1, 1 component times sigma x plus negative nu times 0 plus negative nu times 0 plus 0 times 0 plus 0 times 0 plus 0 times 0. And so that's going to just give us the 1, 1 component times sigma x, and the 1, 1 component is 1 over E. Okay, so that's how we get this relationship, which in a statics course you would have just started with at the beginning of learning about stress and strain, back out of the full 6x6 Voigt notation, account for anisotropy, account for complicated boundary conditions version of this equation. So this is reproducing the simple case here from that general form of the equation. In part B, we're going to have that the stress is equal to 0. So we're going to see how we can get that the strain is just alpha delta T. Well, let's actually work this out. So we're going to start with the strain being equal to the compliance matrix times the stress plus alpha times delta T. And let's put in the full matrix components for this. So we'll copy some of this stuff so I don't have to type it out again, and edit this middle one. Oh, I guess I could have avoided typing that first one too. Anyway, the strain is equal to compliance times the stress plus alpha delta t. And this being the full strain vector is equal to compliance matrix times the stress, except this time the stress is going to be equal to 0. And alpha delta t is not. So we'll put in alpha. Alpha for an isotropic material is just the same as alpha x, or maybe we'll just call that scalar alpha, not vector alpha, multiplied by delta t. So this tells us directly that epsilon x is equal to alpha delta t. Aha. Okay, so now that we've got that, we can work out what the temperature change needs to be to get a certain strain. So we just take that strain and divide by alpha. And this is where we got the 704 degrees C earlier. For the third part, where we have the strain equal to 0, and we want to know what stress shows up when we put that temperature change on it, well, we can notice this stress that we calculated in part A is giving us a negative 1% strain in x, and the temperature change from part B is giving us a positive 1% strain in x. So if we were to add that same stress from part A to the temperature change from part B, and the strain produced from each of those, then we'll find 0. If this one gives us negative 1% in x and this gives positive 1% in x, the sum of those two should give us 0. But let's do this directly. If we suppose rather than just saying the superposition stuff should work and using the strain that we found earlier, we can start off by saying, all right, let's assume we don't know what the stress is, but we do know that it's free in the other direction, so we'll still use this and substitute in that we have 0 in the x strain. In just the x direction, the first line of this equation, if we have 0 and then the kind of like this one and the second one at the same time, then the x strain is equal to 1 over e sigma x plus alpha delta t. That's where that relation we used in the short version of it up above came from, if you want to think of it like that. So in this situation, we've now got the ability to substitute in the temperature change, substitute in epsilon x is 0, and solve for what sigma needs to be. And it's negative E times the thermal strain, which is alpha delta t, and that's supposed to be 1%. So we have exactly the same calculation as we did in part A. Next, suppose it's actually fixed in the other directions. Now we have all of epsilon is equal to 0. So with the rest of the sigma components non-zero, this is going to work out slightly differently, right? It was only the other sigma components being 0 that let us easily multiply the compliance matrix over by sigma in order to figure out how the temperature change is going to be related to the stress. If it's totally fixed in all the directions, then this vector on the left is totally 0. So we'd be better off by multiplying by the inverse of the compliance matrix in order to figure out exactly what the stress is in x. So that's the stiffness matrix. Now in this situation, you can see that the stiffness matrix, because alpha delta t is the same in x, y, and z, we can carry this multiplication out fairly easily. This thing in the front is going to stick around, and then we've got this component, 1 minus nu, times alpha plus nu times alpha plus nu times alpha, and then all multiplied by delta t. That's going to be the sigma x term. Okay, so after a little bit of algebra, we clean this up, and we have that this 1 plus nu cancels with the 1 from the denominator, and we're left with negative e over 1 minus 2 nu alpha delta t. Okay, for gold, nu is 0.4, so this is 1 minus 0.8, and when we divide by 0.2, we get multiplying by 5, which tells us fixing it in the other directions leads to 5 times more stress that shows up than otherwise would. So a thought experiment that we can do here is back in part C, when we didn't fix it in the other directions, the stress by itself, the compressive stress that was causing it to compress by 1% in x, would cause it to expand by the Poisson's ratio times 1% in y and z. So that's 0.4% in y and z. The temperature change that causes it to expand by 1% in x also causes it to expand by 1% in Y and Z. So in Y and Z, in part C, it's expanding by 0.4% plus 1%, so 1.4% total, whereas in part D, we're stopping it from doing that. And if we apply enough stress in those directions to stop it from doing it, it means that that translates to more stress that we need to apply in X by a fair margin. For gold, which has a fairly high Poisson's ratio, it ends up being 5 times higher. Okay, it's also possible to get a lot of this stuff done using a computer algebra system, say Maple, in order to help out with this sort of thing. So let's have a look here. If we end up starting with the stiffness, the Poisson's ratio, and alpha substituted in, then let's just step back and start off with linear algebra. The first couple lines are going to define the C11s, the 1, 2, and the C4, 4, and then type in what the C matrix is. So this is going to allow us to then use this matrix to solve some problems. If we wanted to know what the compliance matrix was, then we could take the inverse of this. So S is equal to matrix inverse of C, and we can try multiplying them together. It doesn't look very nice because of the parameters here and all the decimals that we're dealing with. But if we were to take S dot C and multiply them, then we have basically the identity matrix with a bunch of zeros. So let's try, I wonder if simplify will do anything. Probably not. A little bit. Cleaned it up a bit. So it identified that some things were basically 1. Simplifying more than once doesn't do anything, does it? You've got to play around, right? You've got to try some stuff when it comes to computer things like this to see if you can get things to work. Okay, right. So what we want to do is now try and use this equipment to solve what's going on with the stress and the strain problems that we had up above. So the first thing that we did, I guess this is regular alpha. We can take alpha, we can form alpha vector. Alpha vec would be equal to alpha times 1, 1, 1, 0, 0, 0 for this isotropic material. That's going to make a vector, which is equal to alpha in the first 3 components and then 0 otherwise. Now what we can do is we can figure out what the stress would be if the strain is, if all of the stress components are 0 except for the first one. So imagine that we have sigma is equal to sig x 0, 0, 0, 0, 0. And now we know epsilon is equal to epx, epy, epz, gamma yz, gamma xz, gamma xy. And we wanted to form the equation epsilon is equal to sigma, epsilon well is equal to s dot sigma, compliance dot the stress, plus alpha vector dot multiplied by delta t. Then we can see what this looks like after multiplying out all of the different components. So just knowing that the stress is 0 except in the x direction tells you immediately how we've got epsilon x related to sigma x and delta t. It's a little bit more obvious if we get rid of the material parameters and look at this by itself. So by not substituting in what E and nu and alpha are, then we can see directly how the strains in each direction are related to the x stress and the temperature change in the situation that all of the other stresses are equal to 0. We could redo this same setup if we've got instead that the stresses are all unknown maybe we'll call these ones the shear stress, tau yz, tau xz, tau xy. And then we'll say that epsilon is now 0 except for epsilon x. Actually, let's just make it totally 0. Okay, now we've got the equation that happens when you multiply the compliance matrix by sigma and then add it to the actual alpha vec delta t. You see, the issue is that while we can see from the isotropy of the material that the shear stresses have to be 0 right away, it's hard to tell what all of the axial stresses are because the first 3 of these are 3 equations and 3 unknowns. It's true, if we were to substitute in, if we apply all 3 of them, we can solve them for these unknown stresses and everything, but it's a little bit more convenient to instead work with this equation after manipulating it and solving it for sigma. So we could say that sigma is equal to c dot epsilon minus alpha vec times delta t. This is what we get after rearranging this one and solving it for sigma and multiplying by the inverse of s. Okay, so this equation is a little bit more convenient because it immediately shows us what sigma x is in terms of the other parameters. This is looking a little bit messy, so let's see if we can simplify it and get it to do that same simplification that we found when we were doing things analytically of canceling out this 1 plus nu with the 1 plus nu in the denominator. You can see it in there. Maple just hasn't simplified that. We got a 1 minus nu, and we got a 2 nu over here. If you were to add those together, it would cancel out with what's in the denominator. So we'll throw in a simplify and see if it can't clean that up a bit. Yeah, okay. So a lot easier to read what's going on here. E delta t alpha over negative 1 plus 2 nu, or equivalently a negative e on the top, 1 minus 2 nu, reproducing what we had analytically. Next up, modifying FlexPDE to deal with this thermal and stress-induced strain together, not just the stress-induced strain that we've already got it to deal with. You'll recall that the stress-induced, the stress on an object is related in FlexPDE to net force per unit volume being 0. This is the differential equation we're solving, but it's a differential equation in terms of the actual displacements in x, y, and z at each position by also defining the strains and using Hooke's law. So this was in code looking like the following. So we have the actual differential equations of this net force being 0 by slopes of stress in different directions. And the stresses were defined in terms of the strains, and the strains defined in terms of the displacements, derivatives of the displacements at each point in this solid object. So if we want to modify this to include thermal strain, there's a couple of different things that we can do. We can rewrite the stress as not C times the total strain anymore. If there's a temperature change, it's really C times the mechanical strain. So we could directly modify all the strains by alpha delta t, subtracting that off, or perhaps define the mechanical strain as the original strain minus alpha delta t in each direction, and then modify the Hooke's law equation to, instead of being in terms of the regular strain, be in terms of just this mechanical strain. Or perhaps we could multiply C times alpha delta t and consider this another term to subtract off from the original C times epsilon part of this equation. That would be forming this maybe beta thing defined as C times alpha, form this vector, and then write out what that is as an addition to the stress in each of the directions. All right, example, confirm the analytical results from parts A to D of the previous question. So that's basically find, using FlexPDE for this gold bar, the axial stress required to compress it by 1% in X, the strain for a temperature increase of 704 degrees, the stress if it's held still in X during this temperature increase, how and why. The answer to part C would be different if you held it still in all dimensions during this temperature increase. All right, you can just copy in this code if you'd like. What you'll probably learn more if you do is if you start with something like this, like a previous statics code, and oh boy, and work from that to modify it accordingly. Okay, so here we go. We'll copy that in, and I suppose I should also change the font. It was in large font for teaching, but on this screen it'll be a little bit too much. Okay, so this is code that is doing something totally different right now. It looks like it's doing some beam bending stuff based on applying some stress on the surface. So we'll, on the top of it. So we'll modify this code to be something different and deal with the thermal expansion stuff. What we've got to do that is add in that this is now based on this mechanical strain, and write out what the mechanical strain is. EXM is equal to EX minus alpha delta temp. Can't use delta T because delta T is already written. And EYM will be EY plus minus alpha delta T, and EZM is EZ minus alpha delta T. Okay, now we just need to define what alpha and delta T are, and we'll put that up here. Let's suppose alpha is 14.2 for gold? 14.2 E minus 6, and delta temp we'll put in is 0 at first. Okay, so this should change nothing. Yep, it still works totally fine, is putting out the same deformation that it was originally. Now we'll change it to do the set of the situation that we have here. So, okay, if we've got this gold bar that's 30 in X by 10 in Y by 8 in Z, let's see, we're already drawing out a rectangular prism that goes up to LX, LY, LZ from 0, 0, 0. So we can just change those values and get it to draw this shape. So 0.3 meters, 0.1 meter, and 0.08 meters. Then we'll put in gold's properties, 79 and 0.4 and 19,300. And we've got the alpha in there. Now it should be working, except that the boundary conditions aren't quite right. So we're going to have it free on the Z surfaces. So we can replace these all with load is equal to 0. I'll need this value is equal to 0, 1 for the X equals 0 surface, though. At least in the X direction for now. We'll be changing this up a little bit later. Okay, and then on the X equals LX surface, so right now, just as a check, it's totally load equals 0. We should have nothing happening as a result of it. Yeah, all right, looks like nothing's going on. We can report some stuff right under the plot by saying report val sigma X. Let's imagine putting it at the middle, LX over 2, LY over 2, LZ over 2. And how about the strain as well? Report val epsilon X at LX over 2, LY over 2, and LZ over 2. Okay, so no stress, no strain right now. Let's modify it. So the first thing says, what's the axial stress required to compress it by 1% in X, assuming it's free in Y and Z on all surfaces? To figure this out directly, we can tell it that we need it to compress by Lx times negative 1%. So that tells us that the stress that showed up, this doesn't seem right. The stress is 0. Now I wonder why. Did we say that it is, oh, is this the right, it's the right surface? I got it. Okay, so we are not actually holding it on the other side. We're telling it to move a little bit on the right side, but this doesn't get applied because we overrode it with this other load boundary condition afterwards. So this was not doing anything. Now we're holding it on the left side and compressing it by 1% in X. And yes, we've got 790 megapascals of compressive stress there. We've got no actual strain really. Well, yeah, we've got 1% compressive strain in the center, 1% compressive strain everywhere. That's what we would have expected for epsilon. Okay, great. 1% strain, 790 megapascals, all good. All right. Now, rather than applying that, let's instead say load U is 0 and add in a temperature change. What should happen if we then increase the temperature by 704 degrees? What we should have is no stress, because it's free on the exterior surfaces, yet we should nevertheless have an increase in the strain up to 1%. And yes, we've got basically 1% strain without having any stress. This stress is basically 0, right? This is 101 rather than like megapascals and stuff. This is 0 compared to the order of stress that we typically have. Third situation is to try to hold it still on the other side, value of U is equal to 0, and see what stress shows up when we increase this temperature this way. And we should expect that there's no strain this time. Yep, E minus 10, but we've got 790 megapascals required to hold this thing still. That's the X stress. It has developed some strain in Y and Z though. We can look at what those strains are by kind of reporting this. We said earlier that we expect about a 1.4% strain in Y and Z. Let's check how that works. Yeah, 1.4%. The 1% from the temperature increase that happens in Y and Z, not just in X, and then the 0.4% that happens from this compressive stress translating to Y and Z through the Poisson's ratio. Finally, we can see what the stress that would show up would be if we hold it to a value of 0 everywhere. So let's just put that value to 0, that one, these boundaries. We don't actually need to do this. We could have just specified the first one and then let it carry through to the rest of them. We do need to set it separately on the top and bottom surfaces though. Okay. So now we've got no strain anymore in X, not just X, but also no strain in Y. And we have much more stress required in X in order to make this happen. This is the 3.95 gigapascals rather than the 790 megapascals that was required to just hold it still in X. Final note, what happens if we go back to the previous loading conditions? So here we've got it just fixed in X on the X surfaces, 790 megapascals. We got a lot of Y stress, Y strain going on there. Sorry, not Y stress, Y strain. And imagine we incorporate a little bit more realistic of a loading condition where it's not just fixed in the X direction on this surface and this surface. That would be if it can slide in the other directions. Maybe it can extend there. It's not rigidly supported on this wall. But what if it is rigidly supported? So we get like a full fixed support here that doesn't allow it to expand in Y and Z. That would be setting value is equal to 0 totally on the X equals 0 surface. And we can do the same thing on the other side. What's your prediction for what's going to happen to the stress now? Well, the stress is higher. It's not nearly as high as the 3.9? No. It should be about 5 times the 0.8. So yeah. Okay. So it's not nearly as much as the 3.95 megapascals that we had, or gigapascals rather. It's 8.93 rather 0.893 gigapascals. So this is only slightly higher than the 790 megapascals, 893 megapascals. It is kind of behaving closer to being free, but it's not totally free because the anchors are having a bit of an impact on this. Now here's some other changes we can make. If we make this smaller in X, then the anchors, let's say the wall fixed supports, are going to have more of a bearing. We expect this to go up somewhat. We can change the X length to maybe 0.1, yeah. And now it's a cube. Now holding it at the walls makes it a lot closer to just holding it completely still from moving in those directions. We've got a 1.5 gigapascals there. If we were to take this low enough, then you'd expect that this is going to limit towards the 3.95 gigapascals that we had when we were not allowing it to move at all in Y and Z. On the other hand, if we take X longer, then it's going to limit in the other direction. It's going to limit towards the 790 megapascals as the anchors have less and less of a bearing on this thing. We're exaggerating the displacement quite a lot here from what's being set up. The way we're setting it up, it's always going to be scaled to displace the same. So it doesn't really move this much. It's moving not nearly as much strain as this. This is showing you from the original size of this object, just a massive amount of strain from the scaling factor, but really it's still just this 1.4% in the lateral directions. If we take it smaller and smaller, then you see that it gets closer and closer to the 790 megapascals. So we were at about, oh, look at this, some real numeric issue showing up there. It definitely shouldn't be bending or deforming, should be symmetric, but still is getting smaller and smaller in terms of its X stress. Speaking of bending though, we should be able to get it to bend if we were to modify this to deal with multiple layers of beam. And that's what's going to be our next topic. Just a little bit more before we go on with that, a little bit on further theory for this bending stuff. In Flex, it's not going to agree with the analytical calculations, not totally, unless we've got a uniform stress and strain situation. This is not going to be uniform because of these anchors that are showing up here, leading to a difference in the stress when we're close to the wall compared to towards the middle. So that won't agree totally with what's going on in Maple. But if we ignore the anchors effect, then it could approach what's going on in Maple. You can return to these equations to solve analytically for any missing parameter. Even though we were looking at a situation where the stress is all 0 except for 1 and the strain is all 0 or all 0 except for 1, you could have any arbitrary setup. Like we could say that the maybe the Y and the Z stress are fixed to 0, but the X, while the X strain is fixed to 0, figure out what temperature, how temperature change would lead to coupling and the rest of those things. That would totally be valid. It's ultimately 6 equations and 6 unknowns, and you can return back to this vector nature if you ever need to. Many materials, like organic materials, absorb and desorb water with changing temperature, and this changes size a lot more than thermal expansion for those materials. So keep in mind, depending on what you're dealing with, that this thermal expansion stuff might be the whole story. Some materials have negative thermal expansion coefficients in some temperature ranges, so water pretty famously between 0 and 4 degrees. This is why just like how ice floats because it has a lower density than water, the densest water is at 4 degrees. So if water cools down more than 4 degrees, it'll float up. If water heats up above 4 degrees, it'll float up. So water, this is an interesting effect that tends to make water at the bottom of big bodies of water like oceans fixed towards 4 degrees. And that's kind of interesting. Silicon has a negative thermal expansion coefficient at pretty low temperatures, between 18 and 120 Kelvin. So that might be important to note for you in the future. If you're on some sort of a spaceship and you need to say, okay, what should we do with this silicon? Should we heat up the silicon or cool it down if we need it to expand right now, and it happens to be at only 60 Kelvin, then remember that silicon has a negative thermal expansion coefficient in that situation. So to make it expand, you need to cool it in that range. That could come in handy. All right, over large temperature ranges, the thermal expansion coefficient is pretty temperature dependent. So be careful or include a temperature dependent parameter and integrate to find the total strain that showed up. Finally, non-uniform coefficients of thermal expansion and shear thermal expansion can show up in crystals with less than cubic symmetry. Well, specifically, you can't get the shear thermal expansion for just that. You need to have extremely asymmetric crystals like monoclinic or triclinic. This is, of the crystal groups, these are the ones with the least amount of symmetry. So that's quite a lot of asymmetry required to get a shear showing up just from a temperature change. In order to deal with that kind of asymmetry, we probably want to, we're going to want to set up FlexPDE a little bit differently than we did in the last example, when we just were having it deal with possibly the same alpha in X, Y, and Z, and then only allowing that to modify the axial stress. If we wanted to deal with potentially a different alpha in every direction, then we could go back to our Voigt notation form of the FlexPDE static stuff that we had from what we called general elasticity in 2PO4, and then modify it to include the mechanical strain and thermal strain. So here's our alpha x, y, z, and y, z, x, z, x, y. Then we can incorporate that into changing the strain in all the different directions, just like we did in X, Y, and Z earlier, but now allowing that to possibly have a thermal shear component. And then writing the Hooke's law terms in terms of the mechanical strain instead of just the total strain. Right, so this might come in handy if you need to deal with that. Okay, now on to the curving beams, thermal multimorph sensors and actuators. A material made of 2 layers designed to curve in response to temperature change is a thermal bimorph. In general, any material with n layers that curves in response to some input is a multimorph. Thermal bimorphs have been widely used as temperature sensors for over 100 years. And I'm going to put these videos in the description, so they should be down below. You can click on these ones and check out what a bimetallic strip heating up looks like. So just, if this video doesn't work anymore, then just Google bimetallic strip heating and you'll see what I'm talking about here. Even though, like, if we go back to this previous example and think about it a little bit, the result of this, like, look, let's just consider the numbers in this gold bar. We needed to heat it up by 704 degrees to get it to change in length by only 1%. Now that, we can't actually do that unless we start at a very low temperature for gold, because the gold's going to melt first. So we first have to cool it down and then say, compared to this temperature, if we heat it up 704 more degrees, we can get it to expand by 1%. That's not a very dynamic thing that's going on, because the solid materials generally hold on to their form pretty well. The hardest part about doing that experiment, despite the massive temperature change, might be to actually get the $3.3 million that it takes to buy that gold bar. But so even if you did that, you'd have to cool it down first before you could heat it up enough to get it to expand by 1%. With the aluminum, you have to heat it by 430 degrees, which would not quite melt the aluminum, but it still is quite a lot. And with the ice, you got to heat it up by 182 degrees, which, if my math is correct, means you need to start at about a negative 182 degrees C. Actually, these wouldn't work over that large of a temperature range anyway. We'd have to consider the temperature dependent properties of the thermal expansion coefficient if we really wanted to do this. But my point is that this is a massive amount of temperature change that's required to get a 1% increase in the size of the object. So thermal expansion is not a super dynamic thing. It could be used to give quite a lot of stress, though, because the 100 megapascal scale that we have for these things. So this is like 700 megapascals. 100 megapascal is 1,000 atmospheres of pressure. That's a massive amount of pressure. So stuff's going to start breaking from temperature change a lot before we have a really obvious visible change in its size unless you're measuring it very carefully. That said, some materials do have different thermal expansion coefficients than this and move a bit more, so that can be more dynamic. But if you wanted to make a really good sensor for temperature, then you can instead exploit curvature. Get two objects that have a different thermal expansion coefficient, hammer them together into a thin strip, so that then when one of them tries to expand more than the other one does for a temperature change, it's going to lead to a curvature. First, let's review what we learned about beam bending in the statics course. Okay, so a response to moments, a response to a pure moment on a beam, is a curvature where the curvature caused is the moment divided by the flexural rigidity in the appropriate axis for that moment. Okay, so if you've got a beam extended in X and subjected to a moment about Z, which would cause it to bend in the, let me just get my right hand rule here. If we've got like an X going to the right and you've got Z coming out of the page, Y is up. Yeah, that's right. X cross Y should be Z. Then a moment in the Z direction will make it bend in the positive Y direction as you increase towards the right. If it's fixed on the left, that is. Moment in the Z direction will make it bend up. Okay, so the EI, flexural rigidity, is the integral over the X cross-section of E times Y minus Y bar squared, where Y bar itself is the AE weighted centroid. So the average Y position of the cross-section, where you weight that average with the stiffness of the material. If the stiffness is uniform, then this would just be the average Y value. If it's a rectangle, it's just the Y in the middle. But this is the general formula which deals with non-rectangular cross-sections and which deals with a Young's modulus that is different from one layer to the next. If you're talking about an asymmetric material too, like an anisotropic material, then the E that we should use in this equation is the effective E in the longitudinal direction. That's the E that's going to matter for resistance to bending here. Not the E that's in the Z direction, but the E that's in the X direction in this case. Okay, so in order to figure out how this stuff related to curvature, we looked at local strain when the thing bends into a radius of curvature rho centered on Y bar. Radius of curvature rho means if we're a little bit up above that at increasing Y, we've moved to a tighter radius, and this builds in that the strain is going to be the change in Y above the Y bar, if that's like our neutral axis, the one that doesn't actually bend, multiplied by the curvature. Hooke's law then lets us relate this strain to the stress that's going to show up as a result of this, or the stress that's going to, that maybe is causing this bending. So bending causes a differential force to appear on the surface of sigma dA, and we could integrate this over the whole thing to find out what the moment is. Moment about the centroid is going to be the displacement from the centroid times dF. dF being sigma dA is in the positive direction, so the more we go up times that sigma to the right would give us a moment in the negative Z if we're up because of the right hand rule there. So going up and then force to the right would be into the page. Okay, yeah, so you integrate this over the entire surface and that gives you the moment, right? But when you carry out that integral, you find out that it is just the same equation as we'd have for flexural rigidity multiplied by the curvature. So for uniform curvature, then the moment that is causing it is EI times C. Now, suppose that there's a temperature change as well. How this is going to be different is that the strain is not just sigma over E, but is sigma over E plus alpha delta T. Alpha in the X direction, in the longitudinal direction. So that means we could solve for sigma and end up having this E epsilon minus alpha delta T. And when we work out what this is, picking up the derivation from from this step right here, this lets us figure out that the moment would now not just be this df replaced with E times y minus y bar c, but we'd also have a y minus y bar c plus alpha delta t. And since we don't have that y minus y bar in the this difference in stress showing up from different amount of curvature now in the thermal part of it, this one is not just going to be with a y minus y bar squared after we work out that math. It's going to just be a regular y minus y bar. So we will not have a flexural rigidity in this term that shows up in the first term after we work out how the moment is going to be caused by a combination of curvature and temperature change. What you can do is now solve this for what the curvature would be as a function of not just a moment, but also a temperature change. And let's just look at this equation and see how this works exactly. This is telling us that what would be required, for instance, to get a positive value for this integral? You would need either that the alpha is, so if alpha delta t is constant across the cross-section, then we'd be integrating y minus y bar over the cross-section, but y bar is already the average y. So this integral would work out to 0 if alpha delta t times well, yeah, even if E is different, if alpha delta t is the same everywhere across the cross-section, then this integral is going to give you 0. We've got no change to this, and that should be the case because when we weren't considering thermal expansion, we didn't have to worry about this as affecting as a source of change for our curvature formula. Now, if alpha delta t is not uniform, it will give us a positive result for this integral if this is overall larger, where y is bigger than y bar, and smaller, where y is smaller than y bar. So that could be if you've got a big thermal expansion on the top layer, and then on the bottom layer of this material, you've got a smaller thermal expansion, and everything has the same temperature change. Then we've got the top wanting to expand more than the bottom does. That's what's going to give us a positive value for this, and that will give us a negative curvature. Okay, so it seems like it's consistent, at least in that area. If you've got the top wanting to expand more than the bottom, we're going to get negative curvature, meaning it's actually bending down. To get positive curvature, you need the opposite to be true. You need the bottom of this material layer to be more positive than the top. Okay, once we've got this curvature, we can figure out what the displacement is for a cantilever beam, say, by remembering that curvature is the second derivative of transverse displacement with respect to longitudinal position. So if the displacement stays pretty small, then the longitudinal direction is always still going to be x, and the transverse direction is going to be y. So we can just do two integrals of c with respect to x and end up with the tip displacement being half c times the length in x all squared. Now, I really encourage you to work through this derivation yourself and remember exactly how this thing works, because it's tricky, right? Like this is complicated. And also to do that for the thermal strain incorporation here to see how we get from each line to the next one. Once you do it, you'll get it. If you don't do that derivation yourself, it's just going to be an equation, and you can explore it and you can mess around with it, and that's fine. But you'll never get it quite as much as if you go through and do that derivation, and it's not as scary as it looks. You can do it. Okay, now let's have a look at an example here. Suppose we've got a bimetallic strip cantilever, which is 3 centimeters long, 1 centimeter wide, and 1 millimeter thick. It's 70% aluminum. So with these properties, and 30% tungsten with these properties, find the tip deflection if we increase the temperature by 5 degrees, both analytically and using a FlexPDE simulation. First, let's do the analytical one. I'm going to try and not look at this and just work it out actually a different way than is written there. I just need these numbers up at the top. Okay, so we will build in the equations that we had earlier, but first let's type out the parameters here. We've got length is 0.03. We've got the width, maybe we'll call that B, is 0.01, and we've got the thickness is 0.001. And then we know that the cantilever thickness is 70% aluminum and 30% tungsten. So let's build in some material parameters that are dependent on position. Let's say AL frac is 0.7, and then we're going to say Y mid, the midpoint Y, is equal to H times AL frac. I'm going to deliberately use a different coordinate system than we used in the example here. This one centers the junction at 0 and then builds one material in the negative direction, the other material in the positive direction. But now we're going to center the junction at Y mid, calculate where that is, and then build it around there. So it's going to work out a little differently than it did in the notes. So you can follow this one in the video if you want to see how it works with a little bit different of a coordinate system, and just check your understanding there. Okay, so if that's the midpoint, then we'll say that E is piecewise. If Y is less than Y mid, then we're going to get the aluminum one, 70E9. If Y is greater than Y mid, then we'll have the tungsten one, 411. Oh, wait a minute. I think we're doing this a little bit wrong. If we're less than Y mid, actually, let's first go aluminum, because that's just written out first. So if we're on top of Y mid, then we got 70E9. If Y is less than Y mid, then we've got the tungsten one. And we've got to say that this is 1 minus the aluminum fraction. Yeah. So the junction, if the top 70% is aluminum and the bottom 30% is tungsten, then we're going to have it like this. Yeah, then only 30% is going to be from 0 is where the midpoint is. Okay, yeah. So that much E9, that's the Young's modulus for tungsten. Now, next we've got nu. Piecewise, Y is greater than Y mid, 0.35. Y is less than Y mid, 0.28. And then alpha. Piecewise, Y is greater than Y mid. We're going to have 24 E minus 6 for this aluminum. Y is less than Y mid. It is quite a lot lower for tungsten, 4.3 E minus 6. Okay, so this should be all the material parameters that we need. We don't actually need the density, I believe. So next up, what we're going to do is build in this calculation for the curvature. The first thing we want to do is find the tip displacement when we heat it up a certain amount. So we'll put in the calculation here. So we've got that C is related to the externally applied moment over EI minus 1 over EI times the integral over the cross-section of E, Y minus Y bar, alpha delta T. So we'll need delta T is equal to 5 degrees. We're given that in the problem. And we'll need to figure out what Y bar is and what EI is. And those are defined up here. So Y bar is the integral over the cross-section of E times Y dA over the integral of E dA. That is the E weighted centroid of the object. So we'll say Y bar is the integral. Now, nothing is changing in the width direction. So that means we don't really have to do 2 integrals, but just to keep it clear, we'll put that in anyway. So Y bar is the integral over the area of E times Y from Z is 0 to B, and Y is 0 to H, divided by the same set of integrals, except without a Y. So just integral over E. And we get Y bar is a little bit lower than the midpoint. This has some physical meaning. We expect it to be a little bit lower to the midpoint because the, well, actually not necessarily a little bit lower than the midpoint. This is a little bit of a coincidence because we used 70% for the aluminum fraction. If we'd used 50%, it's going to be a lot lower than the midpoint. That's because tungsten has a much higher stiffness than aluminum does. So the neutral axis is much more on the tungsten side than it is on the aluminum side. Yeah? If we had made this 80%, it probably won't quite be as low as the midpoint. Yeah, it's always around this 0.3 millimeters up. Right. So that's some physical meaning for what y bar should be there. Next up, we need EI. EI is the same integral thing, except what we're integrating this time is E times y minus y bar all squared, and we don't divide by the same integral of E. So there's that integral over the area. There's our EI. What does this mean? It's hard to get a physical feeling for what EI is. EI scales a lot with it depends a lot on the thickness, right? This is resistance against bending. If we make the thickness twice as much, EI is going to scale by like a factor of, let's see, is it thickness squared? We went from 0.2. Does it get 4 times bigger? Nope, it's more than 4 times bigger. It's more like, not thickness cubed. It's a little bit complicated. I think it is thickness cubed, actually. So this one, by increasing it up a little bit, it didn't quite increase. It actually increased by a factor of 8. So if we took this thing and we multiply by 8, yeah, it ends up being thickness cubed there. If we had used a simpler material, then we could have seen more directly that this was working by doing this integral analytically. Even though we're doing it in Maple, it's actually not that bad of an integral, especially if we got rid of the E and the nu changing with position. Then we'd see that this is a lot easier to do. That is, without the material dependent parameters, you can actually do these integrals by hand and work out how what they give you. And you'll recall that EI goes like the width times the thickness cubed, and that's what gives us this scaling that we're getting right here. Yeah. Okay. So next, now that we've got EI, we want to figure out what the bending would be, what the curvature is. So with EI in hand, we can say if MZ is equal to 0, because it's a cantilever, so we don't have any moment applied at the free end, then this is if we're ignoring the weight of the cantilever and all that, then the curvature is going to be MZ over EI minus 1 over EI times the same integral thing, except this time we're going to integrate E times y minus y bar without squaring it, multiplied by alpha, multiplied by delta t. And because alpha is not uniform, we expect that we're going to have a non-zero curvature here. Yes, so we've got it bending down, a negative curvature. Does that make sense? Well, the top material was the aluminum, and the aluminum has a larger thermal expansion coefficient, so we're going to have a negative curvature there, meaning that it's bending down. If we made this 4.3, what do you think should happen? So we've now made the aluminum thermal expansion coefficient the same as the tungsten. Well, now when it heats up, there's no tendency for it to bend up or down, so this should give us a 0. Yeah, so 1e minus 10. But if you make it a little bit bigger, not that much bigger even, like 4.8 versus 4.3, suddenly you've got some appreciable curvature there. If it's a lot bigger, like this 24e minus 6, then even though the individual thermal expansions are kind of small, this curvature can be decently sized, especially if you make this thing very thin. So as you decrease the thickness by a factor of 10, the curvature goes up by a factor of 10. Okay, Finally, we just want to find the tip displacement with this, and the tip displacement is going to be 0.5 times curvature times the length of the beam squared. So for this particular beam, it's going to bend up by 66 microns, and that's not that much, but the length to thickness ratio is only 30. In an actual strip, a more realistic set of dimensions would be making it about the thickness of a decently thick piece of paper. So that's 200, let's say 200 microns, and coiling it up so that the length is like 30 or maybe even 30 centimeters long. Now for a 5-degree increase in temperature, you can get the tip to move by 3 centimeters. And that's a pretty big displacement that you can detect macroscopically. Okay, next up is to check this in FlexPDE, and we'll start with the code that we were just working with and build in the dimensions that, that the problem has. And at first, this isn't going to be doing much because we've got it gold, we've got it heating up by a huge amount. It's not doing the curvature stuff that we need. What we're going to need to do is free it at the other surface except for x equals 0. And now it still isn't going to be curving because we haven't built in the location-dependent material parameter. But we can preemptively determine what the tip displacement is by asking for a report of V at Lx, Ly over 2, Lz over 2. Right. So this will be telling us what the tip displacement is, and we expect right now that it's 0 because there's nothing causing actual curvature here. It's a little bit cut off right there, so I guess I'm reporting too many different things. Let me try that again without this report of, let's say, the X strain and Y strain. Let's just simplify it down, just the tip displacement. What do we get? Tip displacement is negative 8.4 E minus 7. So a very small amount. There's basically no motion in the vertical direction right now. Okay, so let's get it to curve. We'll modify the parameters to just a 5-degree temperature change. We'll change the alpha by, well, now there's a couple of different ways to do this. We don't actually need the density anywhere. We're going to say that AL frac is equal to 0.7, and we'll say H aluminum, or maybe Y mid is Ly times 1 minus AL frac as before. Then what we'll do is we'll say that E is if Y is greater than Y mid, then the aluminum parameters, so 70E9. Otherwise, it's got to be less than Y mid, so we can just use an else statement here and put in the tungsten parameters, 411E9. And same thing for new. If Y is greater than Y mid, then the aluminum one, 0.35, else tungsten's 0.28, and alpha, if Y is greater than Y mid, then 24 E negative 6, not E6, that would have caused some trouble, else 4.3 E negative 6 there. Okay, so let's check if we get some curvature. We're expecting 66 microns if everything is all perfect. Let's see what we get. Okay, it seems like I've mixed up Y and Z in setting up the dimensions of this object, because this is a very different bending of stuff than we expected. Still, we do see that the bending is working correctly. So at high Y, we've got some expansion from the aluminum, and then the the lower y value here. Tungsten doesn't expand as much, so it bends down. Okay. Yes, so I've mixed up y and z, so let's put this as z and this as y. Right, so it bends, and we're in kind of the right order of magnitude, but not exactly the right value. So we didn't get the 66 microns that we expected. We've got something that's a fair bit different than this. We've got 73.6 microns of negative y displacement, negative y because we're bending down. The reason for this is basically numeric error. So we're having trouble resolving this thing because of a couple of different reasons. One thing is the grid density. So we can try to fix that. Maybe 15. I think 15 is about as high as we'll be able to get for this aspect ratio. And still not so great. So 72, a little bit closer. Another thing that we can do is tell FlexPDE to pay attention to the midline position. And we can do that by setting it up, rather than doing it this way, setting it up using regions. So we'll say the aluminum parameters by default. And then we will set up the geometry a little bit differently. First, let's simplify this. We don't actually need those default boundary conditions to be specified, and we don't need to specify any boundary conditions on the Z surfaces. So let's just get rid of that and make it a little bit easier to read. Now we'll say that this one is, let's see, we'll put first aluminum, and the aluminum has got to start at 0 y mid and then go from y mid to ly. Whereas the tungsten region, tungsten is going to start at 0 and go up to y mid. I guess we could have started it at y mid and then go down to 0 as well. That should have worked just the same. Now this likely won't run because the grid size is too dense. And even if we get rid of specifying an n-grid and it tries to make it as small as possible, it can't actually run it. So to figure out how this one works, to see what the effect of doing that was, we've got to change LZ to be smaller, making it thinner in the width direction, which doesn't matter anyway, now allows us to get enough mesh density to simulate this. And this does a bit better. It goes 7.09. Oh, wait a minute. That's not quite right. Value V at the end of this thing should have been a lot closer to what we expected. The reason that we got 0 there is because we forgot to put in the different material parameters for the tungsten. So let's re-specify. E is 411E9, nu is 0.28, and alpha is 4.3 E minus 6. Let's just make sure that we did that correctly. Yes. 0.28, 411E9. Okay. Always double check the parameters. That's one definite source of error there. Okay, so right away, a lot better, a lot closer to the 66 microns. Still would perhaps be better if we could do this simulation in even better detail. And a way to do that is to say, well, you know, since this this Z direction, there's nothing going on in it anyway, maybe we ought to improve the performance by completely eliminating the Z direction. So let's try that. Let's convert this to a two-dimensional problem. How could we do that? Well, we'll get rid of anything that depends on the, we don't need to get rid of the parameters there. Get rid of anything that depends on the Z direction. So that is, yes, this one, and also this one. We've only got one strain left. We don't need that. We don't need this, or the last two, the last terms in this. No more shear that involves Z, and no more W differential equation or Z derivatives of terms in the other differential equations. No more extrusion. And with the grid plot, we won't have any Z or Z specification in this other plot. So I think that might be it. Looks good. Let's check. Oh, we still have a Z here in this global max. Let's get rid of that one. I eliminated a bracket I didn't want to. Okay, there we go. Ooh. Don't need to specify what W is on the boundary either. Okay, so first of all, by changing it to 2 dimensions, the simulation is instant now, right? That's a much simpler simulation to do. And without specifying any n-grid, we've got the thing up to an accuracy of 66.9 microns. 66.5 was the one we calculated there. Now we could increase the grid density and see if it matters. So let's try n-grid is 15. What about 25? How about 55? Can we do that? Yep. So 66.9, still not getting quite better. What about putting a lower error limit? Error limit is 1e minus 12. So this difference is likely not to do with the difference in the numeric inaccuracy, but perhaps something different going on because we're fixing it from being able to expand vertically. We're compressing it here vertically, and so we've got it moving a little bit more, and that means it bends down slightly more than it would have analytically from that calculation. Final observation is this version of going to 2 dimensions, where we've gotten rid of any coupling of the stress from that Z dimension into the X and Y, is equivalent to saying that there's no stress in the Z direction, saying that there's no coupling back in, no stress there. So this is the plane stress condition. If we'd rearranged these equations a little differently, we could have worked it into the plane strain condition, which would be equivalent to saying that it can't move at all in the Z direction.